Okay, 3.3, population growth and resource availability. This is a pretty neat graph of population growth in Italy in the 1700s to the mid 1800s. It's 3D. It looks really cool. You don't have to know how to graph that or read it. Okay, so no population can grow infinitely. The universe is finite. There will always be a limit of something. Some resource is going to run out. Common limiting factors: light, water, space, competition, predation, disease, number of mates, etc. Something is going to prevent unlimited growth. We have intrinsic rate of increase. This is how populations want to grow. They want to grow slowly at first, and then as their population picks up, even if the rate stays the same, now you have more people making more people making more people. So you get into this exponential growth. It starts off very slowly, and then it increases more and more and more over the same units of time. This is also referred to as biotic potential. All populations will grow this way if you put them in perfect circumstances. There's no limiting factors. Now, characteristics that grow quickly, populations that grow quickly. These are populations that can increase very fast. They reproduce early in life. They're born and then they're capable of making babies quickly. Here's an example with people. Each lady is going to have 2 babies, but the ones on the left are going to have their babies when they are 20, as opposed to the lady on the right, she's going to have her babies when she's 30. By delaying it only 10 years, in 60 years, we have twice as many people alive on the left as we do on the right, by just delaying childbirth by 10 years. So the earlier in life you have babies, the higher your population growth can be. Populations that grow quickly have short generation times. The time between generations is short. They're born and they're capable of reproducing quickly. They have long reproductive lives. That means that they spend a decent percent of their life able to reproduce and reproducing, not just capable of it, they are actively reproducing. Something like a bacterium might only live for 2 or 3 days, but it's going to spend almost that entire 3 or 4 days reproducing and making copies of itself. So that it lives much shorter lives than humans, but humans have shorter reproductive lives because they don't reproduce for as much of their life as a bacterium can. Populations that grow quickly have long reproductive lives, and then they have high fecundity. Fecundity is a number of offspring. That can either be number of offspring they have at once or the total number of offspring. The general trend is the larger the critter, the lower the fecundity. When you get to very large animals, whales, humans, lions, they tend to not have many young at a time, as opposed to something like a mouse. The mouse will have several children all at once. And then that goes back to the K and R selected strategies, and we can apply that here. K selected fall on this side. They have low fecundity, high survivorship, as opposed to R selected, which have high fecundity and low survivorship. If we look at these 4 traits, timing of reproduction, generational time, reproductive lives, and fecundity, K strategists fall on this side. Populations of K strategists tend to not grow as quickly as R strategists, because R strategists are the ones that meet these 4 characteristics. Carrying capacity. This is the maximum number of individuals that an ecosystem can support long term. That doesn't mean right now, it means on average. And it is a calculus between biotic potential and environmental resistance. All things want to grow at their biotic potential, which is this intrinsic growth rate. It wants to grow exponentially. But as you approach your limiting factor, you're going to have more resistance from the environment. It's going to apply pressure to stop that growth. Carrying capacity is where environmental resistance is negating biotic potential. Life wants to grow and spread as much as it can. The environment says, no, 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 you need to check yourself. Where biotic potential is canceled out by environmental resistance is your carrying capacity. Carrying capacity can change depending on changes in your biotic or abiotic factors. As the population approaches carrying capacity, mortality increases and fecundity decreases. Okay, this is just general fact. J-shaped curves, J curves, exponential growth, all the same thing. It's this kind of graph where it shows increasing growth over the same units of time. This is based on ideal scenarios, not real life. Then this is real life. This is logistic growth, also called S-shaped graphs or S curves. You still have exponential growth here at the beginning, but then that environmental resistance starts to push and it limits that growth. So it starts to slow down until you eventually hit that balance between environmental resistance and growth. So you get this leveled off point. Carrying capacity is usually denoted as a K. So if you see a graph like this, it might be labeled K, that's carrying capacity. Or if it's not, and you're asked to identify carrying capacity is where this S curve flattens off. Pretty easy. So exponential is fake. This is based on ideal, not realistic scenarios. Logistic is real life. There are two words that you need to know to go along with that. We have overshoot and dieback. Carrying capacity might have a limit, but populations can exceed that. That's called overshoot. You can have population momentum that carries a population beyond that carrying capacity. Then you're going to have things like sickness, competition, parasites, disease, something that's going to limit your population. And then you're going to have a dieback, where your population is now going to dip back below carrying capacity. Now, carrying capacity is usually denoted as a flat line, but populations don't reach a certain point and then stay exactly there. They oscillate back and forth. So carrying capacity, if you zoomed in, really looks more like this little squiggle line. But populations will get just about to this carrying capacity and then stay very, very close. Then we have the formula for calculating exponential growth. These are what each of the variables mean. N sub 0 is the starting population size, your population at time 0. Rate is your rate of growth. E is also natural logarithm, it's 2.7. T is the amount of time that passes, and N sub T is your final population size, your population after your time has gone by. And we have an example with a mouse. Consider a population of mice that has an initial population size of 20 individuals. The intrinsic rate of growth for mice is R equals 0.2 or 20%, meaning each mouse produces a net increase of 0.2 mice each year. Predict the size of the mouse population 5 years from now. Okay, well, we take our formula, we fill in the variables that we know. We do not know the final population. N sub 0 is the starting population, which we know is 20. E is a constant, it's natural log of 2.7, raised to R times T. Our T is 5 years, and our rate of growth, our R, is 0.2. Put it all together, you end up with N sub T equals 20 times 2.7 to the first power, or 20 times 2.7, 54 mice. After 10 years, the only thing that changes is the amount of time. The rest of the formula stays the same. 20 years, same thing. Formula stays the same. The only thing that's changing is the amount of time. Okay, almost done. We have density-dependent factors. These are factors that influence population based on population density. The more individuals you have, the stronger the effect. So if you have more individuals, competition has a stronger effect on your population. If you have more prey and more predators, that's going to have an influence on your population. Too much prey, your predator population will grow. Not enough prey, your predator population will shrink because there's not enough for them to eat. Disease spreads more easily in high density areas. Parasites spread more easily in high density areas, etc. This is called a predator-prey relationship. This is a question that College Board likes to ask about. But what's going on here is it's showing the negative feedback loop of populations change between hares and lynxes. You have the population of lynx increase, but now there are more lynx eating more hares, so the population of hares goes down. Now there's not enough hares for the lynxes to eat, so the population of lynxes go down. The carrying capacity is lower because there's not enough for them to eat. Now there's not as many lynx to eat their hares, So the hare's population can increase. More of their young are surviving. But now there's more hares, so the lynx population can then follow and increase, which then leads to a decline in the hare population because there's more of them being eaten. That negative feedback loop is called a predator-prey relationship, and it's because of these density-dependent factors. Contrasted with that are density-independent factors. These are things that control populations or affect populations, irregardless, not a word, regardless of the numbers of individuals. A hurricane is exactly as strong if there's one individual or if there are 100 individuals. The number of individuals in a population does not affect the factors effect on your environment. The most commonly looked for ones are natural disasters: hurricanes, floods, volcanic eruptions, tornadoes, etc. All right. 4 types of population fluctuation. You have stable. This is where your population reaches carrying capacity and it stays pretty close to that consistently throughout the year. Over here, we have a population of something. Population year-round stays at approximately 1.5 million. It dips above and below slightly, but for the most part, it's 1.5 million. Then you have eruptive. These are also called boom and bust, where sometimes they are stable, but if you have an increase in one of those limiting factors, populations will increase quickly, and then they'll decrease just as quickly when conditions are no longer favorable. These eruptive cycles tend to be more applicable to R strategists because their populations grow quickly, and these stable fluctuations tend to be associated more with K strategists. Their populations don't change as quickly, so it takes pretty significant change to alter the carrying capacity and change the population long term. The third type is cyclic. That's what you see in these predator-prey relationships. You also see them in examples of a population like deer in temperate deciduous forests where you have 4 seasons. A lot of the deer will die in winter. They'll starve, they'll freeze, they'll get eaten, whatever. Spring, they'll give birth, so population increases. Summer, those baby deer become adult deer, so population reaches almost its max. In the fall is hunting season, so some of them will be killed that way, some of them will die naturally, so population starts to decrease again, and that gets you back to winter where some of them will die. Your population reaches the minimum. But then in spring, it's mating season again, so your population is going to go up. It's that cyclical nature that makes it different than eruptive or stable. And then the final one is irregular. There's no recurring pattern. Either there's too much chaos in the system or there's not enough data to have discovered what the pattern is. And then we just have a little funsies graph down here. The relationship between people who cause drama and people who say they hate drama. They usually go hand in hand.